right. I'm really glad they played my intro music. I wasn't sure about that, so that's cool. So yeah, it's really cool to be here in Amsterdam. This theater is amazing, and this is like a true honor to be here speaking, in front of you. My first time to Frontendlove, but I did actually have the opportunity to come to Vue Amsterdam last year. That was pretty cool. So I'm going to be here talking about a couple of things. The first is on offline first applications. And before we start talking about that, we might want to talk about kind of a few things around that. First of all, like what does that actually mean? A couple of things. First of all, we can assume that the core features in an offline first application should basically work with or without an internet connection, and they should also work if you have a slow or spotty internet connection. Second of all, the data you're going to be working with is going to be written in two places. You're typically going to be writing it locally in some form or fashion. This could be a cache or a store, and then you're also going to be probably systematically sending that data to some type of persistence layer in the cloud or some type of database that you're going to be working with. And also, when I say all of the core functionality should work offline, that doesn't mean the entire app should work offline. Typically, these types of applications have a core subset of features that you're kind of developing for that use case, but everything in the entire app, of course, is not going to work offline, just kind of a few main things that you're going to be working with. And then finally, you really, at the end of the day, the reason you're building this is that you want to provide a good user experience to people that are having these situations where they are offline or where they're having these spotty internet connections. Now, the second thing I'm going to be talking about is real-time applications, and we're going to be kind of going into the combination of these two. So what does a real-time application mean, or what is a real-time application? I have a couple of points here. The first is that it's an application that functions within a time frame that seems immediate or very close to that for users of that app. A couple of really good examples that we're all used to working with: chat apps, things like Google Docs, collaboration, anything like where you're working with a group of people that may be working on a single document. This type of stuff is a really nice UX, but implementing these things are really hard, and we're going to be looking at some of the abstractions and things like that that we've built and some ideas around this. And then second of all, you typically are going to be thinking of a real-time application as a distributed system or a cohesive system, because when you're working in this fashion, you have tens, hundreds, thousands, even millions of applications that are running on these devices. When a user makes a change and a user makes a change here and there, these changes might be happening at the same time, kind of solving the problems of merging this data, figuring out whose data should be stored, whose data should be overwritten is a really, really complex problem. And it's kind of something that my team has been working on for a couple of years. So in this talk, I'm going to be talking about some of the strategies that we've come up with for handling this problem, some of the solutions that we've actually brought to the table and open sourced, also some ideas that we're hoping that other people will take and kind of maybe pave the way for more of this type of these application development to happen in the future, because it's a really more common use case as we're seeing for some of the applications that we're building and we're seeing our customers built, and that are really kind of being built more and more often, that it's coming like a first-class citizen, I would say. I'm also going to talk about how some of these apps share, or actually how real-time and offline kind of share certain concepts, where they overlap and how they complement each other, and then challenges and solutions for each one of these scenarios. My name is Nader Dabit. You can follow me on Twitter at Dabit3. I'm a web and mobile developer for about 9 years by trade. For the last couple of years, I've been working on the AWS mobile team as a developer advocate, but also as an engineer and helping kind of drive the future of what is going to be happening within our teams. I've written a couple of books, and the stuff that I'm going to be talking about today is similar to what has been written in this book by O'Reilly, Full Stack Serverless. So if you're interested in some of the stuff I'm going to be talking about, check out that book. You can get it online today. So when you think of AWS, most of the time people think of back-end technologies. Well, there's an entire team of front-end technology that is my team, and that's all we work with. All of the people that are on my team are either full-stack developers or they're front-end developers. The two main different services and features that I work with, or whatever you would call these open source projects, are AWS Amplify, which is a framework for building cloud-based full-stack serverless apps, and then AppSync, which is a managed GraphQL service. And that is kind of what my team does. We kind of build solutions for front-end and full-stack developers. And we're really I would say, trying to kind of enable a new generation of developers that typically are front end, like myself, to kind of be able to build these applications in a fast manner and in a scalable manner. And really kind of being able to take your existing front end skill set and apply that to the cloud. So when I typically kind of started learning about cloud in general or back-end development in general, I was intimidated because I am a front-end specialist and I want to be able to kind of not have to spend a year or 2 years kind of leveling up somewhere. I want to be able to kind of apply this skill set. And that's kind of what we've really focused on. We want to allow people to kind of use their front-end skill set but still be able to build full-stack scalable apps in the cloud. So, into the talk, let's talk about why people would want to build these type of applications. Well, first of all, a lot of these apps would fall into the category of quote-unquote modern application development, but this is becoming more and more just application development. A lot of apps these days are collaborative. They do have chat functionality. A lot of apps have a social, aspect to them in general. Also, we want to make sure that people all around the world can use our apps. This means people in our country that might be like on the subway, or they might be in an area of town without a good internet connection in a basement. But also people all around the world that we know for sure do not have as good of an internet connection as us. How can we build apps that are kind of really going to scale all the way around the world and be able to be used everywhere? Also, these apps typically have a better user experience because when you're building these types of applications, especially the offline first, you're thinking of working with things like an optimistic user interface. So you're writing first to the client, then sending the updates, and then only if the updates failed, you kind of come back and change locally. You're not kind of waiting for that update to happen on the server before you show the user interface updating. So what are some considerations around building these types of things, and what are some of the solutions that we've kind of come up with? Well, first of all, and most importantly, and I guess this is the hardest problem that you may have to solve in this space, is the idea of caching, or just local persistence, I guess, in general. Now, there's this very famous saying, there are only two hard things in computer science: cache invalidation and naming things. So yeah, that was Dan Abramov that said that. Actually, that wasn't Dan Abramov, just checking to see if anyone knew that. Actually, I don't even know who said that, but I like Dan Abramov. So, most of the time when you're working in this manner, you're going to be dealing with these cache challenges on the client. So when you're working with these real-time issues, you do have, of course, the typical server caching, but working with the caching on the client and what all comes to that. Well, a couple of things: data synchronization. So if you have two online clients, they both fetch data. One of them goes offline. User A makes a change, and then user B comes back online. How do you synchronize that data, and how can you make everything consistent across all the different items in the system, all the different clients in the system? You end up doing having typically additional complexity in your code because you're kind of writing code to handle all of these different circumstances. So you have a lot of writing and reading from the cache. You also have cache invalidation locally, and then you have to fetch a new data set from your server. And then complex querying is typically not very easy if you're working from a cache, because typically you have that initial query that gives you that initial data set, and when you want to query from that cache, you're limited by what that initial query was. And I think what ends up happening is a lot of times we start treating our cache like a database, but it isn't a database. But maybe that's what we need. Now, also, with real-time, a lot of the different things that you're thinking about or considerations that you might have, one of the, we're going to talk about a lot of the different ways that you can handle real-time, talking about WebSockets, GraphQL subscriptions, and things like that. But this is kind of just another consideration to take in. How can you actually build this? How can you build this cross-platform? Because a lot of times when you're building applications, especially in the startup world or in large corporations and stuff, you're going to be building for the web, but also for native iOS, native Android. You might have desktop, you might have cross-platform solution that you're working with. Then there's conflict detection and conflict resolution. Conflict detection is detecting when there is a conflict between two pieces of data that need to be written, and then the resolution is the resolving of that conflict. How should you handle that? And then we talked about, or I mentioned really briefly, multiple platforms. How can you build these types of applications across all the different platforms that you'd like to be working with? And then finally, scalability. So if you're working with just a handful of clients, this typically isn't too sophisticated to do. But what about when you are dealing in a fashion where you want to scale your app and you need dozens or hundreds or even thousands of connected clients? So what are some solutions for some of these problems? So first of all, caching. If you've ever worked with GraphQL, you may have worked with something like this when you're doing a few different operations for a single mutation. First of all, you have the mutation itself. This is what's writing to the database. So you're taking some data, sending it, and storing it. Then you're creating an optimistic response out of that data. So you need to be able to take that cache, create a mutation, which is basically the optimistic response, and then you end up then writing to that cache. So what ends up happening here is that you have a lot of complexity. Again, you have a lot of complexity in the amount of code you're writing, but also in the logic there. Someone comes in here and you have a lot of this code happening in your app. You just have a lot of mental, taxing that happens as people come in there and try to make changes and things like that. So essentially, what you're doing is you're writing twice. But the real, in our opinion, sweet spot is just writing once. So that's kind of where we're going to be getting in just a moment. But there's also this idea of cache hydration that you end up having problems with, because when you come online, you typically are going to be fetching that initial data set. But down the road, you might want to have more sophisticated queries against that data set. So you end up having the problem of not being able to do that because you're working with just a single data set that you've worked with. And you might be fetching that entire data set and then working locally with different maps, operations, whatever array operations that you're working with to filter out the data that you need, which is not ideal. So at the end of the day, maybe we don't actually want a cache. Maybe what we want instead is a store. What if we, ideally in a best case scenario, had something extremely, extremely simple? Something like this. Let's think about every to-do app that we've ever built. We go in, and it's something really basic, because when you want to learn something new, you need to make it basic, right? Think about a mental model like this, where we have an object or some data structure that is our initial state. We want to make a change. We write to that state. We want to make an update. We write to that state. We want to read something. We query from that state. Pretty simple. It's really straightforward, and it's the best way to kind of get up and running. What we've decided is, this is a very good mental model to work with, so how can we take this and scale this to kind of work around all of these different problems that we have? And what we've released is something called Amplify Data Store, but I'm going to talk about what we've done and what is open sourced out of this and what is not, and hopefully people can kind of take the part that is not open sourced and maybe build other backends for it. But also, if you're interested in checking it out, you can try it out. And it's basically a really end-to-end solution for building these types of applications, full stack, front and back end, but also across clients like native iOS, native Android, web, React Native, so on and so forth. And the way this works is that it all kind of revolves around that mental model, that programming concept of writing to a local data model. And you're no longer writing to all these different places. You're going to be only writing to this single data store API. And from there, all of the work of synchronization is kind of handled for you by the system. And we decided really that GraphQL schema definition language was a really great way to do this, because it allows developers to kind of model the data within their application like they would a typical data model, because a GraphQL schema looks very much like a class or any type of other classical data structure that we've worked with in the past. And the idea is really like this. You define your data model in GraphQL. We then take these models and we kind of translate them to the persistence layer of choice and then create models out of that GraphQL schema. We'll look at it a little more in depth right here, so let's walk through it. You are the developer. You create a GraphQL schema. The schema could be a type of post or whatever your app might look like. This could be, and typically is, a lot bigger than this, but for this example, let's take a look. So you create your schema. You then run a build. Now, this build is typically an NPM script if you're a JavaScript developer, like most of us are. But if you have a native developer on your team, it might be something like an Xcode build phase or a Gradle script or something like that. Out of that build, we create a data model. And this data model will allow you to then use our Fluent interface that I'm going to go over in just a moment to then interact with your backend. And this will be generated in whatever the language construct of choice of your platform. So if you're on web, this would be TypeScript or JavaScript. If you're on native iOS or native Android, that would be Java Cocos or Swift. And you're now operating using this new Fluent interface where you're saying, I want to store .save, I want to store .query, and then we're going to look at how all this stuff is then kind of persisted to the backend for you. So for mutations or writes, you would say something like save. For queries, it would be something like store.query. You can then also work with predicates. So what would a predicate look like? Let's say we want to query and we want to define some type of predicate, like we only want to get this or that out of the query. And these predicates can be also chained together. So you can say, I want to get all of the posts that equal this title and that equal this publisher. And these predicates also apply to deletes. So you can say, I want to delete every item that has this title or that equals this property. And then deletes, again, also kind of work the same way. So let's take a look at the vertical slice of this architecture. After you create a model instance, the library will basically decompose that model instance and create in what we call the storage engine component, a model registry that kind of contains all of those models based out of that GraphQL schema. And then there's an adapter, and we do this using a classical repository pattern. And this will convert into the persistence layer of choice. So we'll automatically detect the platform that you're on. If you're on web, this is going to be IndexedDB. If you're on native iOS or native Android, it would be something like SQLite. And then if you're working with React Native, we have two different adapters that we're working on. One that's already out for async storage, and the other would be a React Native bridge into the native platform itself. And you can actually use this without any AWS account. So this is all the open source part. This is the front end part. So if you really just want a nice way to do data modeling and programming against all of these filters and things like that using this Fluent interface, you can kind of stop right here, and you can then maybe just work with it locally. This has nothing to do with like AWS. This is just an open source project. But if you do want to sync everything, we have a flag that you can just flip locally by using the Amplify CLI. And this will then take the sync engine and kind of connect it to the storage engine. And from there, you can then start using the entire system. And what we end up doing is kind of converting the reads and mutations to GraphQL operations. So a read would be a query, a mutation, a write would be a mutation. And then we have observables, so you can observe the model. So say we want to observe a post. Anytime someone makes a change, create, update, or delete, that observable will be triggered, and we get the information back to our subscribed clients. So that's kind of the cache part. So let's talk about the real-time part. So what are some real-time options that we have out there? First of all, long polling. This is not the best way to do things. It's by nature inefficient because you're going to be overfetching or underfetching because you're not really doing this in any sophisticated way. You're just saying every 30 minutes or every 30 seconds, I'm going to pull the server. Then there's service and events. These are a little bit better, much better actually. These kind of would be in the same category as WebSockets. You don't hear as much about service and events, typically because they're limited to UTF-8 as far as like what data can be sent across the wire. There's also a limit of 6 concurrent connections. A few other limitations that kind of go along with service and events, but the API is actually cleaner and nicer to work with than WebSockets. But with WebSockets, we have a lot of abstractions that are out there. So if you want to work with WebSockets, there's libraries like Socket.io that make this a little better. And then with WebSockets, you can actually also transmit binary data that you cannot do with service and events. But what we decided to go with was GraphQL and GraphQL subscriptions. And GraphQL subscriptions are event-based, so typically a subscription can be triggered to fire when an event like an update, create, or an update or create or delete. So you can say on create post, I want to get that data. And when you want to set that up, you can basically create a subscription query on the client, passing in whatever subscription that you want. And then there is a connection that's made, a two-way connection from the client to the server and back from the server to the client. And the implementation of a GraphQL subscription is actually up to the developer. Typically, you see this done in WebSockets, but it can actually be done whatever way you'd like. And using the Fluid interface, you can now just say, hey, I want to subscribe to this model. Anytime this happens, anytime a change happens, we're going to just let you know, and we're going to give you all the information out of that change. So you'll get the model, you'll get the operation type, and you'll get the data itself. And what this allows you to do is that big cache that we were looking at earlier looks something like this for subscriptions even. Instead of kind of having to do all this work, again, is kind of being done for you on the back end. And what we're able to do is have this idea of a single rehydrate query. So we can say we want to subscribe to the data, and anytime some data has been changed, we know that it's already been successfully merged to our local store. So we can then just refresh or re-render our application and show that data to our connected clients. Next, we have conflict detection and conflict resolution. The basic idea behind conflict detection and resolution in all different strategies and ways that it's being discussed is typically you just want to provide a way to merge concurrent modifications always and in order. So what are some scenarios that this might be necessary? We have a couple of users all connected. A user makes an update. The update gets sent to the other connected clients. Another user does the same thing. Everything is great. But what ends up happening is when we have multiple updates that happen at or near a concurrency, when someone makes a change at the same time, and then we end up with a lot of connected clients, and then this just becomes more and more complex. Having a real strategy around how to do this is what will kind of bring additional complexity and make your user experience better if you can get this to work right. So what typically this comes down to is tagging objects with some type of metadata. And there's a couple of really popular ways that if you kind of look and read and see all of the ways that people are doing this, there's two main ways that people are typically doing this. Operational transforms and CRDTs, which are conflict-free replicated data types. You can see who's using these. Google Docs actually uses operational transforms, but CRDTs seem to be the more recent innovation that people are kind of moving towards. And most of these strategies come down to this idea of a clock. And some of these clocks are really academic, so if you start going down these rabbit holes, some of them are very hard to understand, in my opinion. But what we decided to go with is this idea of a monotonic counter. And if you even read some of the papers on this, it seems more complex than it is, because really all it comes down to is like having a version that only goes up or only goes down. So a monotonic counter might look like version 1, version 2. Version 2 can never go back to version 1. It can only go up, or vice versa. You might have a decreasing monotonic counter that only goes down. This conflict resolution and detection strategy is completely controlled by our system, AppSync. We do this by using GraphQL types with versions that are used for merge or reject decisions. And we also do this with an idea of two different tables. So we have a base table that contains all of your base data, and then we also create a ledger or a change table that contains all of the operations that have happened within this system. Every single write, every single update gets logged into this change table. So the versioning looks something like this for the monotonic counter, something really basic. Version 1 then goes to version 2, so on and so forth. And the change table looks something like this, where we keep a primary, a primary key by kind of merging this primary key in, or I guess we have like a unique key done by merging the primary key and the secondary key, which is the combination of timestamps and unique identifiers. And what this allows us to do is this conflict resolution strategy called auto merge that we kind of called auto merge ourselves. This is something like a CRDT or whatever. And the way this works is this. Let's say we have two connected clients that are online at the same time. User B creates an operation. This gets propagated to user A. Everything is fine. No crazy stuff happening yet. Let's say user B goes offline and they create a mutation. Ideally, this is what you would want to happen. User A also comes online and they make a change. So here we have a conflict. The conflict is in two places. First of all, the age is 35 on person A, but it's 34 on person B. And then the second conflict is user B is adding a new field called location. So how do we manage this? The way that this happens is this. User B comes back online. We then detect that that user is online, and we're going to send an update, and we're going to merge using these sync-enabled GraphQL resolvers. And we're going to say, hey, this new field that wasn't there before, let's keep that, but let's not let the user that made the update before this user overwrite the data that shouldn't be overwritten. So what you end up with is this nice union of the two different fields where you have the data that you want, everything else has been discarded. And the way that we do that, again, is we use that combination of base tables and change tables and GraphQL types for versions and detecting and defining the merge and reject decisions. And there's a couple of other ways that we offer also. So you can do auto merge, but you can also have a complete control over that with a Lambda function. And then we have optimistic concurrency, which is essentially last writer wins across the entire object itself. I'm almost done here. I'm a little bit over on time, but I'm going to go ahead and try to finish this right now. The last piece of this is really sync. So synchronization is kind of the idea of this. Let's look at a really typical scenario where we have two connected clients. One goes offline, a change happens, they come back online. What you might do naively would be to kind of take the connected client that was offline and then fetch all of that data again. Now, this seems like it might be an okay approach, but what ends up happening is when we're working with a lot of our big customers that have a lot of data and they also have a lot of complexity on their client, and they also don't want to spend any extra money querying and having extra data across the wire. But this also comes a lot down to when we're talking about, having speed and low latency. If a user comes online and they have a good connection and they fetch all that data, and then they have a low internet connection, we're fetching all this data again, the least amount of data is better, right? So we've come up with this idea of delta sync, and this is implemented into our system as well. What ends up happening is this, just like before, user comes online, fetches all the data, they go offline. When they come back online now, though, what we're going to do is we're going to send a last sync operation, a last sync argument into the actual query itself. So we're going to say when they first sync, we want to get that timestamp, and when they come back online from being offline, we're going to pass that last sync in as an argument. And what we're going to then do is only query the data that's been changed since that last sync. And that way we only get the data that comes down that is changed, and we're not querying the entire database again. And then finally, this enables quote-unquote time travel, because when you have a ledger of all of your operations, you know everything that's happened. You can then go back and see when this piece of data changed, when that piece of data changed. And then finally, the last thing that I would say that we kind of think is really great about this approach is database optimization, because we also have a time to live on that ledger. Because you might say, hey, we're keeping all of this data, why are we keeping it? Like, that's going to become a very big data set, and that's true. So there's a time to live, and then the time to live will automatically delete these items based on how long you set that. So that could be 30 minutes, could be 30 days, it's up to you. And then after that time goes away or goes by, we delete those items for you. So the platforms that we currently support are native iOS, native Android, web, and React Native. You can check out more about this at this Amplify Data Store docs. So just Google Amplify Data Store, you'll get this. Also follow me on Twitter, Dabit3, and I have a bunch of blog posts and stuff about that. And that is it. Thank you so much.